So, in the last lecture we discussed about the new generation offshore platforms. We spoke about buoyant leg structure, it is a form defined new kind of platform. We also spoke about triceratops, we spoke about non ship shaped FPSO and so on. So, what are the important aspects which have been discussed while these new forms of offshore structures have been generated? Let us look at that. So, we spoke about BLS, triceratops, of course 3 legged tension platforms, tension based TLPs and of course non ship shaped FPSO. We will discuss each one of them separately about the dynamic analysis when we move to the next module. But let us here see these structures have innovative structural form, that is very important. The structural form is new, the structural form which has been developed is new. Actually these forms have been selected in such a way that they can alleviate the loads and ultra deep waters, maybe a depth of about 1800 meters and so on. The functional use of these platforms remains same as that of the existing platforms. There is no deviation in the functional use of these platforms when compared to any other conventional offshore platforms. You have got to maintain the similarity. Then what is so special about these generation platforms are form defined function. So, based upon the form I define the function. Whereas in earlier generation platforms function was fixed and form was generated. For example, steel jacket platform, what was the function? Drilling, production, storage were the functions, they were fixed and forms were selected to accommodate all of them. Then slowly, for example in FPSO there are many alternatives, there can be floating, production, storage, there can be floating, storage and offloading, no production. So, these are all form defined function, because for that form production is not possible, is it clear? So, there has been a complete deviation in the selection or design of an offshore platform based upon how to suit a different depth or greater water depths, what we call ultra deep water depths. What should be my form which is comfortable for existence in these waters, and for that selected form what functions can I have? I may have production, I may not have production. So, there has been a deviation, right. So, this deviation fundamentally occurred because I am selecting a form to suit my existence or stability or survival of the platform for different water depths or greater water depths. Subsequently, the maximum possible functions are accommodated in that chosen form. So, obviously you will see there are certain platforms which are meant or called as new generation platforms may not provide all functionalities as you had in earlier platforms, they are choosy. Okay. So, all these makes them different from that of the conventional platforms. Any questions here? So, we have quickly seen different types of offshore platforms, their structural action and their growth or adaptation to the design or modification of the existing design to suit various functions, various water depths, etc. Okay, how the structural geometry was altered to cater to different kinds of preferred structural actions under the given loads. That is the evolution what we saw in the previous 4 lectures. So, nevertheless in this lecture we will discuss something about coastal structures also, because they also form as ocean structural systems, we must understand them quickly, and of course the structural action related to coastal structures. Okay. Then we discuss about the dynamics of single degree mathematical model systems. We go ahead with how to mathematically model these as a single degree freedom system, as a multi degree freedom system, how to identify the dynamic characteristics of these systems, and how I will use them for my dynamic analysis. Is that clear? That is what the provision what we have in the first module of lectures. Okay. So, we discussed a very important part in the first lecture. We spoke about mass of the platform, we also spoke about rigidity or flexibility or stiffness of the platform indirectly. We also spoke about material which are commonly used for offshore platforms. When I said material, we quickly discussed about the damping characteristic of material. We also highlighted something about non-linearity, which can come from the material behavior or it can come from the loading behavior. What we have not seen so far is very interestingly the right hand side of the platform. For example, I am so far talking about all platform characteristics. Okay. We have not discussed about the external characteristics, which is nothing but force. What are the different kinds of forces? Why is it a function of time? If the force is not a function of time, do we have to do a dynamic analysis? So, that is a very fundamental question which everybody has. Is dynamic analysis related to variation of the force coming on the system with respect to time, or even for a static force, if the response of the system is respect to time, do I do dynamic analysis? So, this will be answered. Okay. It is very important. All the time, for all the structures, for all the loading systems, you may not have to do a dynamic analysis. So, when do we do a dynamic analysis? So, dynamics is a property with varies with time. Okay. So, time characterization of any behavior is what we call as dynamics. If the variation is not phenomenal, it is marginal, it is called quasi static. If the variation is not there at all, static analysis. Is that clear? So, there is a path of analysis what people have followed in the literature. When do we do dynamic analysis? We will address this slightly later, but we must understand that can my mass, stiffness, damping and f of t contribute to dynamic analysis. So, it is very important for all of us to understand all these are called essential characteristics of dynamic analysis. So, if you want to know what are the essential characteristics of dynamic analysis, dynamic loading, I must say mass of the platform or mass of the proper material or the member should exist, the stiffness should be there, damping should be there and f of t should be there. Instead of saying mass, stiffness, damping and force, we will rename them slightly when I move forward. I will call them as inertia force, restoring force and damping force and forcing function. I will just rename them, but I will use the same concepts back again in the down the lectures on somewhere down the line when I talk about mathematical modeling. Okay. So, we will talk about in this lecture quickly an overview of coastal structural systems and their structural action, because this is also important for us to understand, but we will not talk about the evolution of coastal structural system as we did for offshore platforms. So, the focus is on offshore platforms in this course. If you want to really know what have been the form evolution of coastal structural system, probably this is not the course which will address you that. Okay. Anyway, nevertheless, we will talk about different forms and their functions and the structural action for our understanding. Any questions here? Any doubts on the previous 4 classes, what we have discussed so far? Any difficulty for anybody? So, do not have to be so serious, though I mean you are not recorded lively, we can edit it also, there is no problem. Let us take it as a class, it is very important. It is not that we are projecting or making a movie, it is a class. You have got to pass the exam, you have got to get a grade on this, remember this, most important. So, be casual and whatever doubts you have, you can always ask. Now, do you have any doubt? Still if you do not have a doubt, either it should be extraordinarily clear or it is of no use for me, sir. I am waiting for some more information of the same order which is of totally useless to me, so I can get a good grade in this course and clear away my course. It is going to be mathematical based, as I said. PPT will be only about 10 to 15% supportive, 85% remaining will be mathematics. I do not want to introduce the dose in the first lecture because I want to, the last date of withdrawing the registration is I think 19th or 23rd. I am waiting till that time. So we cannot withdraw, then I will push mathematics into that. Okay. So I will wait till that time, slowly we will move, show you some good photographs and videos, and people may think this is all about dynamics, you can go ahead with that. The moment you say you go ahead, a green flag is shown, then we will take you to the yellow, red and etc. But be sure that whatever we discuss here will be, to the best of my knowledge, it will be transparent and clear. I will explain what the best I know, and if you have not understood anything you can ask me, we will clarify it further, we will make it easy and simple, that is very important. Okay. So do not have to have a very high degree of seriousness, it is a class, so be in that format as you have been otherwise in other classes. So we will talk about the coastal structural systems now. Coastal structures, we are not addressing the evolution of the structural system, the reason, the basis. Nevertheless, we will talk about the purpose, why are they constructed, where are they constructed, not geographically but physically, what do you mean by a sea wall or a dike etc., because these are all common terms which generally come across to you when you talk about dynamic analysis of ocean systems. So we must know this. Okay. So what are the essential functions of a coastal structure? It is built to protect the shore from wave attack. In the previous case the functions were to either produce or explore or test oil from the deep sea, but here it is to protect the shore from wave attack, to prevent erosion and other similar damages caused to the shore from the wave action, to retain sand for a long shore transport, that is another function of a coastal structure, to reduce the inlet filling because this will cause large amount of dredging if you want to avoid that, to hold down or protect the mooring vessels which have been housed along the seashore, maybe offloading vessels, maybe cargo vessels or passenger ships, whatever may be the case. I need a structure to hold down them or hold them, jetties for example, and so on. Coastal structures are also useful in coastal defense schemes, it is very important because one of the strategic type of structure which is constructed for coastal defense or protection systems. Of course, to prevent flooding in many countries, to provide sheltering of harbor basins, to stabilize navigation channels, it is a very important way of transport and communication between different channels and inlets of every country, to protect importantly the water intake system which supplies water, or outfalls which disposes water or any other effluent to the water body, and so on. Coastal structures are generally used in coastal defense schemes. The main objective there is to prevent the shoreline erosion and the flooding of the hinterlands. So sheltering of harbor basin, harbor entrance against waves, stabilization of navigation channels are also important as one of the function of the coastal structural systems, which are all the essential objectives of these kind of structures. So first type of its kind is sea dike, the photograph what you see, both of them are related to sea dikes. We will talk about the important features of a sea dike. Sea dikes, the basic structural form is trapezoidal. The basic structural form of sea dike is trapezoidal in shape. It is essentially constructed to maintain the desired slope so that erosion does not take place, that is a function. Generally sea dikes are very long in length and very high in cross section. So trapezoidal cross section expected to be massive, okay, gravity based systems, massive structural form. So, the moment I say massive, what is the proposed material which comes in your mind when you talk about sea dikes? Boulders or stones, okay? Boulders or stones or rocks of large volumes, etc. Okay? So, the material essentially is fine material in clay over granites, etc., or large boulders. Sometimes the surface also finished with grass, asphalt, etc., to prevent erosion on the top side. So, that is what you saw in the last photograph. This is a cross section. You can see here the slope prevention mechanisms can be of different vary. You can have a filter, you can have a closed covering layer, you can also have grass or grains growing on the top, you can have a submerged sweep, etc. If you have a low tide, you can have a submerged bank. This is what we call a submerged quay. You can have different kinds of surface protection systems like asphalt covering, like grass or vegetation, like filter, etc. All these are called sea dike surfaces. Sea dike is essentially a massive structural form which is used to prevent shoreline erosion. So, different geometric forms of sea dike for different slopes. You can say the inward slope is 1:10, the outward slope or the leeward side slope is 1:3, and so on. You can have an asphalt covering, you can have a rubble stone covering, you can have a grass, etc. Same thing what we saw in the last slide. The functional aspects of sea dikes are the following. They are low permeability structures. They are watertight, essentially built for protecting low lying areas against flooding. That is the essential function of a sea dike. Essentially the construction material are sand, silt and clay and boulders. The seaside slope is usually gentle, 1:10, whereas the other side is 1:3. The essential reason is it should avoid the wave run up and impact caused by waves. So, the seaside slope is gentle, 1:10, 1:15. The other side is around 1:3, 1:5, etc. Okay. That is the geometric form what we have for sea dikes. Any questions here? So, the material essentially is boulders, clay, sand, minerals. The layer can be rubble stones, it can be asphalt layer, it can be grass as well. So, one of the protection system used for control flooding or protecting the lower land from flooding. The second type is what we call as a sea wall. It is as similar to that of a retaining wall, but what is then a difference between a retaining wall which retains soil with that of a sea wall? These are two different kinds of pictures of sea wall what you see here. One is of course having a vertical section, other is having a sloped section or a stepped section. The one is having a stepped section here, one horizontal step, and there is one more horizontal here. The width may be lesser than this, but it is a different section, whereas this is purely vertical on one side, otherwise it is completely sloping. Okay. Typical onshore structure with the principal function of again preventing flooding of the land, and the structures begin the storm surges and waves. That is the essential function of a sea wall. Again, as you see in the material, essentially it is rubble masonry, stone rubble masonry or random rubble masonry. It is generally constructed parallel to the shoreline. Wherever your shoreline, it is constructed parallel to it. It strengthens only certain part of the coast. It is not constructed all along the coast. Wherever it is weak, wherever the sediment transport is severe, wherever the erosion is very high in its volume, during that section only it is being constructed. Okay. Essential function is to prevent shoreline erosion. So, two geometric forms we saw, horizontal, sloped horizontal, or simply one way horizontal, one way sloped. So, it can be horizontal, sloped, horizontal. So, cross section can be vertical, of course with an horizontal and a slope. So, this is the sea side, this is the land side. So, this can be essentially a rubble masonry, which is material essentially used is stone or boulders. So, we can also say it is a massive structure. So, it actually protects the natural beach profile, that is an important function why these are constructed. It protects the natural profile of the beach from soil erosion. So, what is the structural action of this? It is highly vulnerable to toe scoring. There can be a severe scoring at the toe of this. Okay, human leg, heel, toe. Similarly here, this is heel, toe, this is heel. So, there is a enormous amount of scoring happening here. This results in overtopping of this. If scoring happens. So, this causes instability to the wall. To protect such problems, they are constructed along with the groins. Groins is another type of structure. We will talk about this slightly down the line now. They are constructed integrally with the groins to protect them from scouring or toe scouring. So, wave slamming, surface run up and overtopping are critical action responsible for structural failure of the sea walls. Sea walls generally fail because of slamming, surface run up and overtopping. These are the failure modes or reasons why they fail. So, sea dikes, sea walls. The construction aspects of sea wall, if you look at quickly, they are classified as sloping front and vertical front, as we saw. Sloping front are constructed as flexible rubble mount structures. They have flexibility to overcome the toe and crust erosion. The stability of the slope depends on intact toe support. So, there are some toe supports also constructed along with this to prevent the erosion in the toe area. What we call as armored slopes, this is what we call as armored slopes. Armored is nothing but surface layer is strengthened, armoring is strengthening. We are again describing the sloping front rubble mounted masonry structures. These are the different geometric forms which are available for sea walls. The beach side is in all the cases here, this is a design beach, this is the toe area. You can also use geotextiles, you can use rock underlayer, overlayer, etc. These are different methods by which the surface erosion on the sea wall area can be protected. Any questions here? So, there are two basic geometric forms of sea dikes and sea walls. We have discussed them and we have quickly discussed what are the problems associated with the structural action of a sea wall or a sea dike, how they can be protected and what is the form of a structure. It is a massive structural form of a specific cross section. The function already we know, flooding and overtopping, etc. How do we strengthen is what I said, the return wall or a toe wall. You can see here in this sketch, you can see the wave return wall being constructed to strengthen the crust area. Sometimes even in this area toe wall is additionally constructed to protect the toe erosion. That is another aspect by which this can be protected. The mouse movement is not coming here, it is coming, okay. So, this is a vertical front sea wall sketch what we have. The mass concrete generally is on the front face, then the sand filling happens which prevents the original profile of the beach, and over this people sometimes do asphalt covering or a concrete covering to make it accessible and neat, as we saw in one of the pictures in the beginning of this. Okay. The other type of construction what we do for coastal protection is revetments. Revetments can be as porous as this, as porous as they are, and you can also cover this layer from surface erosion using geosynthetics or geotextiles. Okay, either way you can do that, because the surface is essentially constructed for slope stability. So, to stabilize this slope, either I can reinforce it in this design pattern, or I can do it using a geosynthetic or a geotextile. So, revetments more or less have a similar geometric form as that of a seawall. They are again onshore construction structures. The principal function is protect the shoreline as similar to that of a seawall. It is constructed with cladding of stone, concrete or asphalt, and then the slope is armored to maintain the natural shoreline profile. The armoring can be either in a rubble line or it can be a geotextile or geosynthetic lining, depending upon the functional requirement of that area. The typical cross section of a revetment, you can see here the vegetation layer is covered by the, on the tip there is a bluff stone which actually protects the soil erosion in this segment. Then there is a choke stone, and then this layer is armored, which we call as an armor stone and a filter stone, because there can be some surface runoff which is coming from the surface which can be collected and then drained off. Okay. That is why we have a filter stone there. So, typical cross section of a classified revetment which has been done for shoreline protection. So, essentially the material is again rubble masonry or stone with a combination of concrete, asphalt and vegetations. The other type of structure is bulkhead. Bulkheads are structures intended to retain or prevent sliding of land actually on the beach side, not to maintain the profile of the beach, whereas there is a possibility that landsliding may happen on the shoreline of the beach. Okay. To prevent this landsliding, one construct what is called bulkheads. It protects the hinterland against flooding, and the wave action is of secondary importance. So, it is essentially the retaining action coming from the soil. Okay. It is protecting the land from sliding. So, the wave action is not a primary importance in this kind of structural action. It is designed and constructed similar to that of a soil retaining structure. The common structural form is a simple vertical wall anchored with tie rods. That is the fourth structural form what we saw for coastal structures. The functional aspects of these structures are different. The geometric forms are more or less similar, but the size in terms of its length, dimensions, cross sectional area or the surface treatment are different. So, they are generally constructed in the mooring facility areas in the harbours. Bulkheads are constructed in that segment. So, it is a small segmental area where they are constructed, whereas in other cases they were on the large lineup along the shore, whereas here they are near the marinas or harbour areas to minimize the wave action. So, that is the structural form which is recommended for a bulkhead. Essentially it comes with the soldier pile which is then sheathed to the surface, then use a filter cloth and a refill where you can collect the surface run of water and drain it off. Then there is an anchor pile which is connected to the sheathing which stabilizes or offers stability against the action in waves or water. So, the primary function is to prevent the sliding of land near the marinas or harbour sections. So, it is a simple rectangular form, not for an infinite length, for a specified length in the marinas and harbours where landsliding has got to be protected or prevented. The other type of structure, as we saw, to protect seawall also they are constructed integrally. These are called groins. These are some of the sketches of groin structures. Interestingly, groins are built to stabilize the stretch of a natural artificial nourished beach against erosion. The functional aspect is as same as a seawall against erosion. They are generally constructed where there is a net longshore loss of beach material is being seen. Okay, there is a longshore sediment transport occurred. So, in those sectors groins are constructed. Functions effectively for longshore transport when it is being seen. The structural form is straight, but interestingly they are perpendicular to the shoreline, not parallel. Okay, they are normal to the shoreline, whereas sea walls are parallel to the shoreline, groins are normal perpendicular to the shoreline. Again the structural form is a rubble masonry, trapezoidal in cross section and so on. Generally groins are constructed in series, not a single groin is constructed. This is what we refer as groin field in the literature. Okay, the literature says you must not construct a single groin, you must construct series of them. This is referred as groin field in the literature. They are the most interesting difference between a groin and a seawall is that one is parallel to the shoreline, whereas groins are normal to the shoreline. The structural form is almost similar, structural action is almost similar, material of construction is almost similar, functional aspect is slightly different. So, we will quickly go through the slide. Well designed groin systems can arrest the slowdown rate of the longshore transport, that is the essential function of a groin. Building a material in a groin bay provides protection to the coastline against erosion. It is used to hold artificial nourished beach material sometimes as one of the additional function of a groin. If at all you have any questions in this area, it will be only about the structural form and the function, not on the name or any other activity. Please do not be panic about, because we are not discussing in detail about the coastal structures in this course. This for completeness we are addressing this. Our essential topic is dynamic analysis. As I said, immediately once I have a massive structural form, the structure becomes stiff. When the structure becomes stiff, the response of the structure to wave action is lower. It may not be important to study the dynamic analysis of this at all, but there are structures which are floating also, for example floating breakwaters. So therefore you must understand the coastal systems also parallelly, that is why we are discussing this. So do not be panicked that we are discussing about the different kinds of structural forms, where we will not attempt to discuss the dynamic analysis of them. Okay. We will quickly pass this. There are different shapes, T8 etc. Rubble groins are most popularly used. They have reduced the risk of scouring and formation of strong rip currents. So this has been identified in the literature that rubble groins have been successful. So we have also recommended series of groin field along the Marina coast, Marina Beach coast in Chennai, which is a post tsunami study what our department did for Government of India. Professor Sundar and Sanna Siraj did this design. So when you walk around the Marina Beach extend near the Chennai Port Trust, you will see that lot of groin field have been established as a post tsunami effect of Indian coast. So it is basically a rubble groin, it is a series of groins constructed for land protection against wave attacks. The projection dimension is generally determined by the surf zone width. We are not talking about this in detail here, because we are getting into coastal hydrodynamics. So that is not the focus of this lecture anyway. So what we are interested is the cross sectional dimension, the location, purpose and structural action. We are just looking at the glossary of these kinds of structures, that is all. There are many classifications in terms of shape, terms of height, maybe high and low etc., depending upon the sediment transport etc. Terminal groins, permeable groins etc. are also different classification for different kinds of littoral transport as discussed in the literature. We also have something called breakwaters. This is nothing but a detached breakwater there can be a continuous breakwater. Detachment is here, you can see they are constructed with a gap in between them. Structurally this gap should be not more than 50% of the length of the breakwater. So if you do not want to have them continuous, you can even break them. So you can see here these are all breakwaters constructed with a gap, but interestingly when you construct a breakwater which is detached, you will have a specific form of sediment occurring which is there in all the beaches. Okay. So that is a counter effect of construction detached breakwaters on the shorelines. They are small, relatively short, non-shore connected, near shore breakwaters. The principal function is to reduce the beach erosion. They are built parallel to the shore just on the seaward side in shallow water depths. Okay. These are critical points which you must remember when we talk about breakwaters, because we will talk about floating breakwaters now. So there are multiple detached breakwaters spaced along the shoreline which can offer protection to the substantial shoreline frontages as seen in the literature. Gaps between the breakwaters are in the most of the case of same order of magnitude as the length of the individual structure, maximum 50% of the length, or worst by worst is equal to the span of the breakwaters itself. Breakwaters reflect and dissipate some of the incoming wave energy. It is very important because if you want to reduce the wave energy potential near the coast, breakwaters serve that purpose as well. It reduces wave height in the lee of the structure, reduce shoreline erosion. The material used is rubble mound, as we see here, rubble mound structures with a low crest which allows significant overtopping. These are some examples and photograph of rubble mound breakwaters. You can see the material here. Most commonly applied type of breakwater in the recent past. Simple shape is mound of stones. Homogeneous structure of stones are the general form of this construction. They are large enough to resist displacements due to wave forces. So they are massive structure. So the structural action because of the wave in this type of structures, if it is massive rubble mound, it is insignificant. If made highly permeable, it may result in penetration of waves and of course sediments if present in that area. So there can be a sediment transport possible if they are made permeable. So there are problems associated with permeable breakwaters. This is a functional problem. We are talking about the structural action here. So our focus is not on the functional aspect of this. Conventional system is a rubble mound structures which is consists of a core and a finer material, then covered with an armor layer. We will quickly skip this, not important. Sometimes the armor layer can also be of concrete lining, where you have got a rough wave climate. These are different structural forms in the cross section for different kinds of rubble mound breakwaters. So what we discuss here is some important dimensions which we will talk about slightly later. This is a wave action, this is my SWL level, these are my slope 1 in n. What should be the value of n? What we must see here is the slope on the leeward side and the other side are different. This is m and this is n. This is my top width, this is my crest width, this is my base width, etc. So one can have a rubble mound breakwater system with GS, can have a submerged breakwater where the SWL, the still water level, is above the breakwater crest itself. Can also have seawall with a GS core and a backfill separately done. Can also have a similar type with a quarry run. Quarry run means the filling is of a different material here. This is a GSE core level. So the core is different here, is the rubble mound core, whereas here it is quarry core, nothing but a sand, quarry sand. So you can have different kinds, submerged, protruding, or a seawall combination. The geometric form is more or less trapezoidal, massive type of structure. You can also have what we call as reef breakwaters. They are in principle designed as a rubble mound structure with submerged crust. The crust is generally submerged. Both homogeneous and multi-layer structures are constructed for reef breakwaters. The principal objective is to prevent beach erosion, but the crust is submerged. The principal function is reduction of wave height at the shore. Two important aspects: beach erosion is prevented and wave height is controlled when you construct these kind of breakwaters. They are built coast parallel, they can be long or short, essentially submerged structures, allow enough amount of overtopping. The objective is to reduce the wave action on the beach because the wave height is controlled. Wave breaking is also controlled because wave breaking exerts force that is being controlled by these kind of breakwaters. Essentially material is rubble mound, homogeneous pile of stones, or sometimes people use concrete armor units for surface lining of these breakwaters. The shape is itself is stable because a massive unit. We will quickly skip this, we are not talking about this. You can have a submerged sills, it is another kind of structure. Submerged sill is another kind of ocean structural system. Sill is a special version of a reef breakwater built near shore, it is a special version, it is a classification of reef breakwater. This is essentially used to retard offshore sand movements by introducing a structural barrier at one point on the beach profile. The sill may also interrupt the onshore sand movement as well. So, this will vary the shore sediment transport when this kind of structures are constructed. They form as a barrier. Sill actually introduce a discontinuity into the beach profile, so that the beach behind it becomes what we call perched beach. They are also used to retain the beach material artificially placed on the beach profile behind the sill sometimes. I will show you a cross section here. They are essentially materials again rock armored rubble mound structures, or sometimes these kind of structures are also available in a prefabricated formats. So, you can use prefab units for this submerged sills. So, these are some of the next items of classified structures in ocean systems, which is jetties. The essential function is for stabilizing navigation at the inlet points. So, to stabilize navigation, jetties are constructed. They are shore connected structures, generally on either side or both sides of the navigation channel. They are constructed normal to the shore, extending into the ocean. They confine the stream of tidal flow at the inlet points. Therefore, the possibility there is to reduce the channel shoaling, and it also decreases the dredging requirements. So, wherever you have got sand accumulation or sediment transport heavily occurring, jetties can be constructed to reduce the sediment requirements or dredging requirements, and of course, it reduces what we call channel shoaling effects. These are different kinds of geographic locations where a jetty can be proposed. Extended offshore of the breaker zone, jetties generally improve the maneuvering of ships also, because they provide shelter to the ships from the storm waves. So, jetties have functional requirements. Structurally it is concrete, material essentially is concrete resting on piles. Essentially it is concrete resting on piles, usually long structural systems. I should say continuous, not only long, continuous structural system, there is no break. they are similar to breakwaters in terms of its functional aspects. So, we have additional references, I want you to look at these to have more information, because I slightly made this lecture faster. Manga Carsten, Shoreline Management Guidelines DHI, Aronson Cox, Design and Performance of Weak Breakwaters. There are papers by our own faculty colleagues Velu, Sundar and Sanna Siraj, Ocean Engineering. Yamato, Moved Floating Breakwaters, Response to Irregular Waves. There are many interesting references which you can read. Now, interestingly, we will quickly look at 4 tutorials. I want you to answer them as an offline for this class. If you wish, you can submit them, because remember, all tutorials which have been submitted by you will be kept as a record with me. In case your performance goes bad in the quiz, we will use this as a trump card to support your marks. Even if it is recording, we will eliminate this from the recording, because then this talks about the evaluation system of IIT, so that is not right. So, you submit the tutorials to me, I will keep it aside, sincerely attempt your exams. We can substitute these, because anyway this can be easily openly copied, you have got a lot of literature available. So, what best you can do is write it neatly, only handwritten material will be accepted. All drawings has got to be drawn by hand, no copy paste of photographs, you have got to draw them. Draw them with or without color pencils, that is up to you. Hand sketch, draw them, explain the perspectives of these in terms of the question which is being asked. So, let us quickly look at the tutorial sheets. Write a brief history on offshore industry. So, do not look this as a social studies class, though the term sounds as history. So, what I wanted is a different history, which I think I explained. Write a brief history of offshore industry. What do you understand by the term GSPR? How is it significant in oil and gas exploration? List few fixed type offshore platforms that are constructed. I want the name of the platform. You can give additional information, name, year of construction. If you know more information about it, it is good, but try to give them basically the name of the platform and where are they constructed and when are they constructed. Name few offshore fields and their approximate year of installations. There is an error here, we will correct that later. Name few offshore fields and their year of installations. What are important features of a fixed offshore platform? The structural action is very important for us to understand. What are the important features of fixed offshore platforms? Write a brief note on any one fixed offshore platform, any one platform, pick up from the literature, expand it and try to explain it in detail. This is tutorial 1. We got 4, we got only 10 minutes more. I am not passing a copy of this, it is not essential. I think I have been talking for 50 minutes, we can at least write for 50 minutes. So, there is no need for a copy of this. You may not even submit this, you have the full liberty of skipping this. So, you can take a challenge of your performance in the examination and then you can skip this. Second tute, name few fixed offshore jacket structures, name few. What do you understand by gravity based structure? Do not expand it, do not abbreviate it. I want what do you understand by this? Why it is called gravity based system? What are the key points of a gravity based system in terms of its structural action? We discussed this in the class. Of course, draw a neat sketch of a gravity platform, underline the word neat. List important parts of a jackup rig, we explained this type of platform as well. what are the salient features of a compliant platform. We elaborated it in 2 lectures, so you must be having detailed understanding of this now in terms of its structural action. So, one can explain this. Can we move to the next slide? I want you to draw a neat sketch of a guide tower and of course mark the parts. I think we will understand what is a guide tower, why it is called as a guide tower, what are the problems associated with the guide tower, talk about fatigue, talk about touchdown point, talk about the lead, fair lead, talk about the anchor drags, etc. Next tutorial 3. What are salient features of ATs, articulated towers? What do you understand by articulation? It is nothing but a deliberately introduced joint, okay, hinge, pinned connection structurally. What are salient features of an AT? How it restores, because the guide wires are now removed, but it restores under the wave action because of the buoyancy chamber, and provision of ballast chamber introduces stability of this platform. How, why, we have discussed this. So, what are the salient features of AT? Draw a of course neat sketch of this and mark the parts. Draw a neat sketch of a tension like platform and mark the parts. What do you understand by TLP mechanics? Offset and set down, how does it restore its normalcy under wave action, what we call as a TLP mechanics. Then discuss features of semi submersibles, what is the typical depth at which TLP operates, look into the literature and then quote, do not guess. Then discuss about spar platforms, different types of spars, cell spar, truss spar, etc. Though we skipped it faster in the last lecture, but still these are open source literature, different types of spar platforms. Then how about the water depth at which semi submersibles generally operate, quote examples. Can we move to the next sheet? Can I give a comprehensive lookout of different types of platforms at different depths? Just to draw a line diagram, starting from shallow depth to ultra deep waters. Last tute, what is an FPSO? Apart from abbreviating it, explain each part of F, P, S and O. What do you understand by offloading? List few offshore platforms meant for exploratory drilling and explain their features. For example, drill ship, for example, which are meant for exploratory drilling, not for production. So, we close it here. So, I want you to answer these 2 sheets at your own interest offline, then submit it to me, we will keep it as a record. If you have any questions on this lecture, please ask. So, the next lecture we will talk about the mathematical modeling, move into single degree of freedom systems. Oh, you want to write, that is fine. I thought you were going to ask me a question. Oh, you are copying down the question, that is okay. As long as you do not ask me, I have no problem at all. So, these initial 5 lectures will give a comprehensive walkthrough of different kinds of platforms, their structural action, their functions and coastal systems as well. So, with this as a base, we start now understanding dynamics of single degree freedom system models in the coming lectures for about 11 lectures more down the line. Possibly we will stop at that point for quiz 1. Okay, thanks.